Hi students, welcome to metallic bonding, which is our next chemistry topic. This is based on chapter 5 of our current textbook, so you should be having a look at it as we go as well, and you'll find lots of resources on our OneNote as well. So let's get into it. This is following on from ionic bonding, so it's our next bonding model, and it explains the bonding between metallic elements, so the elements on the left hand side of the periodic table. Remembering, ionic bonding was when we were bonding metals with non-metals. So what are the properties of metals? And so we'll go through the properties of metals just to make sure we're all clear, and then we'll explain the metallic bonding model that attempts to explain those properties. Now, all metals have what's called luster, and luster is it's a description of how it reflects light, basically. And so metals typically will have a shiny surface when polished. They don't necessarily keep that shiny surface, so something like aluminium, when it's polished, is very shiny, but then very quickly oxidizes to aluminium oxide, which gives a dull finish. But other metals can polish up quite nicely and stay polished for a fair amount of time. They are good conductors of heat and electricity. We make lots of uses of that, and so that's a pretty obvious property of metals. They are what's called malleable, and that means that they can be hammered, bent or rolled into any desired shape. So if you've ever seen a blacksmith working on something, you would have seen them treating the metal with its malleable properties. It's the same as if you get a piece of wire and bend it. You can bend it, that's the thing, it doesn't snap, which is the opposite to malleable, being brittle. Ductile, another term, and what that means is it can be drawn out into a wire. So you can make copper wire, you can make gold wire. Basically what they do to make those wires is they heat up a chunk of it and then they squeeze it through small holes, and it can be drawn out into very thin wires. Generally have high densities, so they're dense. So for their occupied volume, they have a large amount of mass. Have a range of melting points, but are usually quite high. So there is a little bit of warning there. There is a range of melting points, like something like mercury has a very low melting point, being a liquid at room temperature, but most of the metals are quite high. That's why we can use them in pots and pans and things, and in other applications. Are often hard and tough with a high tensile strength. Tensile. Meaning that they offer high resistance to stresses of being stretched and drawn out, and are therefore do not easily break. So when you get a piece, if you have a steel ruler, or in this case a fork, I just happen to have one here, okay, you can bend it and it goes back to its original position and it doesn't snap or break. And if I was really strong, I could try and stretch it and it wouldn't really stretch. It's why we use steel or metals in building bridges and sky rises and all sorts of things. It's because of its high tensile strength. So here's a table of the properties, some of the properties we just mentioned. And this is what's the inference about the structure is. So the property must tell us something, must give us some clues as to what the bonding within metals are. And people have been able to make these inferences for many, many years, even before we knew what the actual bonding was, or could investigate it. So metallic luster, that means there's something on the surface of solid metal that is an excellent reflector of light. Now, we don't know much in physical science about light, but light is a very strange thing. Hi guys, got a little bit interrupted. Someone knocked on the door. Hopefully I can remember where I was at. We were talking about why things have metallic luster and about light. Okay, in physics light's made up of photons and things, and we don't need to know how that works, but for something to be shiny, it's got to interact with those photons. And we'll come up with a model that explains this property. And the other properties, good conductor of heat, Well, there's something inside a metal that can carry or pass on heat energy along its structure. Now, what exactly is heat energy? We'll look at that when we explain it. But something you can heat up, you can have a metal rod and have one end under a flame, and that heat will transfer along the metal rod and you'll feel that at the other end. So the model, to be a successful bonding model, has to explain that property. Good conductor of electricity, so there's got to be charged particles free to move, basically. Remember ionic bonding? To conduct electricity, you've got to have some free charges so they can move. Let's see if I can just get rid of that taskbar. Go away. You're not supposed to be there. Okay, made it disappear. Oh, the metallic lattice. What does it look like? Like a bunch of oranges. It's a good analogy. Here's a carton of oranges. They're all the same size approximately. You put them in the box, you shake them around, and they will set themselves into this ordered structure. And you have the oranges there, and then you have the gaps in between. Okay, and then underneath you've got an orange there, an orange there, an orange there. So you've got a similar regular structure, and underneath this orange is a hole. Now that's a good model of the metallic lattice, because what we're saying with the metallic lattice is that the atoms in metals are arranged into a lattice structure surrounded by what's called a sea of electrons. What do we mean by that? Well, the metals, because they form positive ions and they have a small number of outer shell electrons, those outer shell electrons become free in a metal, in a solid metal, and they're free to move around. And that means that the metals which have lost, all these metals have lost their outer shell electrons, so they all have a positive charge. So these are the representations of the cations, and the delocalized electrons, or the sea of electrons, are whizzing around. So these guys are the oranges, and these are little electrons, little negative charges whizzing around. Now, if you took away these green negative charges, you'd have all these positive charges, and they would repel each other, and it wouldn't be stable, because positive electrostatic charges repel, or like electrostatic charges repel. So these negatives which whiz around, they are like the glue that holds it all together, because this positive cation is attracted to this negative, this negative, this negative, this negative, this negative, this negative, and so it just jiggles around in its spot. Whereas this one also jiggles around in its spot, because it's surrounded by all these moving electrons, and the electrons are moving in all different ways. And so the cation is attracted in that direction, and then attracted in that direction, and just jiggles around in its position in the lattice. And this is what's happening in a solid metal. And this is the model that we're using, the metallic bonding model. So again, here's another diagram. Here are our cations, the valence electron attached to, so these valence electrons are attracted to all these cations. So this is the initial contact. So this is when we're making a solid metal. So the atoms come in from molten metal, cools down. The atoms have outer shell electrons, and as they come closer and closer together, these outer shell electrons suddenly find themselves attracted to these other nucleuses. Then, once they reach a certain stage, these electrons are stripped off, form the cations, and although they're shown here as static, they're actually moving around, constantly moving around. And these dashed lines represent the force of attraction at this instant that the delocalized electrons experience. And so as they're moving around, these dashed lines would move correspondingly. And you still got the cations. Okay, so electrostatic force of attraction, metallic bond. Here's another one just showing you the ordered arrangement of the cations, and again these little blue dots, the mobile valence electrons or delocalized electrons, are whizzing around inside it. And Again, you can draw it like a lattice, but that's not a really good representation. This is just iron, where you can see that the iron cations are all regularly arranged. So metals can occur as crystals. If you have a lattice, if you have a regular structure, it's a crystalline substance. What do metal crystals look like? Here's a beautiful crystal of metal called, or a metal compound called pyrite, which is actually a metal sulfide. I think it's metal. I think it's pyrite, but it's cubic. And this expression on the outer surface is an expression of what's happening on the atomic scale in the way that the cations are being ordered. Got another picture, I think. Here's some more. This is another metal, and we'll actually do a prac where you'll look at metal crystals growing, and you'll see what they look like. So to summarize, when metal atoms combine, a lattice is formed consisting of cations in a sea of delocalized electrons. And it's the electrostatic attraction between the cations and the electrons that is the metallic bond. Now the next video we'll be looking at the metallic properties and what they are and how we explain them and relate them to the lattice structures. So cheerio.